All right, welcome to The Explainer. Today, we are embarking on a really fascinating journey together. We're looking at how we are teaching machines to literally see the world. We're going to explore the incredible story of how cold, dark code is being transformed into true artificial sight. So, let's dive right in.
First things first, let's get our definition straight. Computer vision, or CV, isn't just about plugging a camera into a motherboard. Cameras, well, they just capture light. CV is about interpretation and understanding. We're essentially giving a machine a visual brain that comprehends data, allowing it to recognize faces, track movement, and make really complex decisions based solely on what it sees, pretty much exactly like you and I do every single day.
To really wrap our heads around this, we're going to anchor this explainer with a specific story. Picture a fully autonomous, self-driving car trying to navigate a chaotic, busy city intersection. Pedestrians are darting across the street, traffic lights are flashing, other cars are swerving unpredictably. What does the machine actually see in that split second? As we go through this, we'll follow this car as our main protagonist to understand exactly how it digests the visual world.
But before we put our car in drive, let's quickly map out exactly where computer vision sits on the artificial intelligence family tree. The absolute broadest category here is AI. Within that, we have machine learning, and zooming in even further, deep learning. Nested right inside deep learning is our focus for today, computer vision. It's a highly specialized application that's distinct from things like text processing or robotics, even though it often acts as their eyes.
Okay, Section 1, the power of machine sight. Let's explore the initial awakening of our machine as it begins to process the physical world around it.
Moving into Section 2, the journey of an image. This marks the literal, step-by-step process our self-driving car uses to digest a single frame of that chaotic street we just imagined.
So here's the first half of that journey. Step 1 is image acquisition. That's the physical hardware, the camera's actually snapping the photo. Moving right to Step 2, pre-processing. Think of this as the machine putting on its glasses. It cleans up the visual noise and adjusts the contrast so it can see clearly. Then, in Step 3, feature extraction, it really starts to pick apart the image. Now, it's not looking for a car quite yet. It's looking for the edges of a bumper, maybe the round shape of a tire, or the specific red glow of a traffic light.
And that brings us to the real climax of our car's thought process. In Step 4, object detection, the system takes all those extracted shapes, draws bounding boxes around them, and successfully classifies them as cars, pedestrians, or road signs. Finally, Step 5, decision-making. The car takes all that categorized visual data and makes the absolute crucial decision to stop, turn, or keep going. Keep in mind, this entire 5-step narrative is happening in a fraction of a second, on an endless loop. Pretty wild, right?
Section 3, the Computer Vision Toolkit. Because to make this rapid-fire story even possible, our car relies on some very specific algorithms, which have evolved massively over time.
There's been just a monumental leap in how these tools operate. If you look at older, traditional methods, using algorithms like edge detection, they're kind of like manually tracing a picture to find features. I mean, they were effective, sure, but super slow and rigid. Compare that to the modern era, deep learning methods. We're talking incredibly fast models like YOLO, which actually stands for You Only Look Once. Instead of manual tracing, these models intuitively recognize complex patterns in real time, giving our car the lightning-fast reflexes it desperately needs to avoid a crash.
Our car is actually utilizing a whole symphony of these modern techniques perfectly in tandem. It uses optical character recognition to literally read the text on a stop sign. It uses object detection to locate multiple pedestrians on the sidewalk. It might even use something like pose estimation, which detects human body joints to predict if a cyclist's body language means they're about to swerve into the lane. It is multi-layered comprehension happening instantaneously.
Section 4, Real-World Vision Applications. Let's see how this technology builds beyond just our self-driving car story, expanding these visual superpowers across huge global industries.
The real magic of this tech, it's continuous automation. See, an algorithm will happily stare at millions of images on a manufacturing line without ever getting bored, suffering from fatigue, or, demanding a coffee break. This unblinking speed is completely transforming everything from quality inspection on factory floors to monitoring highly secure environments.
Take healthcare, for example. The exact same story of feature extraction we just walked through with our car is helping doctors save lives right now.
By feeding X-rays, MRIs, and CT scans into a computer vision system, the AI assists in rapid, accurate disease diagnosis. It can often spot microscopic anomalies way faster and far more consistently than the human eye ever could. And out in the fields, computer vision acts as this unblinking eye in the sky. Using drones equipped with vision sensors, the agriculture industry is monitoring crop health across massive distances. It instantly detects which specific plants need water or are falling ill, which allows farmers to apply treatments with literal pinpoint accuracy.
But honestly, this tech isn't just out on a farm or in a hospital. It is already in your pocket. Retailers are using it for automated cashierless checkouts to track what you put in your bag. And on your smartphone, a computer vision algorithm is making complex feature extraction decisions every single time you use Face Unlock to open your device.
Section 5, Blind Spots and Future Challenges. Because every powerful story has an antagonist, right? And for computer vision, it's the severe technical limitations we're currently facing.
Make no mistake, this is not a perfect system. It has very real physical limits. If our self-driving car hits a heavy shadow, a bad rainstorm, or if an object is even partially hidden, what's called an occlusion, the algorithm can easily get confused. Plus, teaching these models requires absolutely massive datasets and exceptionally high computational power. Building a functioning digital eye, not cheap and definitely not easy.
And beyond just the immediate physical environment, there are deep structural data challenges. A machine only knows what we teach it. If a model is trained on a limited data set, it's going to struggle immensely with unpredictable edge cases in the real world. Think about it. A self-driving car trained exclusively in sunny California might completely fail in a snowy Canadian winter. It requires continuous, resource-heavy retraining to adapt to new environments.
So, to wrap up this explainer, I want to leave you with a final thought on this incredible journey from dark code to artificial sight. We have seen how machines learn to interpret our world, from spotting stop signs in chaotic intersections to diagnosing complex diseases. But as we continue to overcome these technical blind spots and teach machines to see the world perfectly, what incredible new frontiers are they going to help us uncover next? Keep questioning the technology that's shaping our tomorrow, and I'll catch you in the next one.